We, the team Illuminator from KCG College of Technology. We are here with the conceptual design for powering the Red Planet, a sustainable energy solution for Mars. Our mission objective is to develop a battery management system that works efficiently in Martian atmosphere. Designing solar panels for Mars presents several challenges due to the harsh Martian environment. Low solar irradiance necessitates larger and more efficient panels, while dust accumulation requires frequent cleaning or anti-dust coatings. Extreme temperature variations demands robust designs. Weight and space constraints necessitate lightweight and compact panels, potentially compromising efficiency. Dynamic tilt angle optimization and effective dust cleaning mechanisms pose technological challenges, while integrating solar panels with other energy sources and storage systems requires sophisticated management systems. Mars presents a number of challenges for solar power system operation, including a dusty atmosphere which modifies the spectrum and intensity of the incident solar illumination. Also, degradation of the array performance takes place due to dust deposition and low temperature operation. In order to overcome the environmental challenges for Mars solar array operation, the irradiance model of the Mars must be analyzed thoroughly. The irradiance model of Mars refers to the study and calculation of the amount of solar radiation that reaches the surface of Mars. This is an important aspect of understanding the Martian climate and environment. The irradiance on Mars is influenced by various factors, including the planet's distance from the Sun, its axial tilt, and the presence of the thin Martian atmosphere. On average, the solar irradiance on Mars is about 589 watt per meter square, representing only 43% of the average irradiance observed at Earth's surface, which is 1361 watt per meter square. The perihelion of Mars results in the highest solar irradiance on Mars, reaching up to 715 watt per meter square. Conversely, aphelion of Mars results in the lowest irradiance, around 492 watt per meter square. For powering the UAV, we propose to use tandem. A tandem solar cell is a specialized type of solar cell that stacks multiple layers of semiconductor materials with different band gaps. This technique aims to maximize energy conversion and improve overall efficiency. We also use a maximum power point tracking to optimize the output of the solar panel and to ensure maximum power extraction from varying environmental conditions. The solar cell which we selected is monocrystalline half cell. The manufacturer is Teleson and the part number is TP7F78M H590. The cell characteristics are described in the table, such as short circuit current, open circuit voltage, diode saturation current, quality factor, series resistance, and parallel resistance. When we consider the Martian atmosphere's temperature, the average temperature is of minus 63 degrees Celsius and minus 81 degrees Fahrenheit. And the temperature dependence and panel configurations are described in the table. For simulation purpose, we have taken the value of minus 63 degrees Celsius as the average Martian temperature is of minus 63 degrees Celsius. Now we will see the power requirement. The power required for a drone on Mars depends on several factors that include size, weight, operating altitude, flight duration, and specific design. But the key factors include drag force, lift force, propeller efficiency, operating altitude, and flight duration. Our conceptual design drone's mass is around 50 kg. By considering all the maneuvers such as hovering, cruising, and ascending, the maximum power required will be around 500 watts. The average power consumption will be around 375 watts while assuming 75% of average consumption, and the energy requirement will be 1875 watt hours for 5 hours of flight duration. This is the simulation model we have used to obtain the IV and PV curves. We have used a PS constant block to give the value of irradiance. We have used a solar cell. The part number of the solar cell is TP7F78M H590. We have used a current sensor and voltage sensor to measure the values of current and voltage. We have used a PS Simulink converter that is used to convert Simscape block to Simulink block. The ramp block is a fundamental element used to generate a linearly increasing or decreasing signal over a specified time interval. To the ramp block, we have connected a variable resistor that allows to determine the IV curve, identify efficiency, and investigate the effects of various parameters. This helps in load testing, power regulation, and implementing MPPT for optimizing solar energy systems. We have used a product block to multiply the values of voltage and current to give the value of power. We have also used a solver configuration that is used for simulating dynamic systems. The solar cell is connected to the electrical resistance, that is ground. Finally, we have used two workspace block that is used for capturing and analyzing the simulation data. All the outputs such as voltage value, current value, and power value is connected to the two workspace block. The Simulink model is ran for three different irradiance values, one at aphelion, that is 492 watt per meter square, another at perihelion, 715 watt per meter square, and the average irradiance of 589 watt per meter square. After running this Simulink model successfully, in the command window using the plot function, we obtained the IV curve for three different irradiation models. Also, we obtained the PV curve for the same three irradiation models. From this graph, we can infer that the maximum power output is around 530 watts at the perihelion of irradiation value of 715 watt per meter square and the temperature of minus 63 degrees Celsius, that is being the average temperature of the Martian atmosphere. At the same time, the minimum power output is around 360 watts at the aphelion for the irradiation value of 492 watt per meter square and the temperature of minus 63 degrees Celsius. After obtaining the PV and IV curves, we calculated the power available from our system. By using the basic formulae, we came with the power available of 397.5 watts and the energy available as 1987.5 watt hours. And these values are sufficient comparatively to the power and energy requirements. And the maximum power available is around 530 watts. And the maximum energy available is around 2650 watt hours. The future works for our project includes developing algorithms that can adjust the tilt angle in real time based on changing weather conditions, dust levels, and other factors. Also, combining tilt angle optimization with intelligent energy management systems to ensure sufficient utilization of solar energy. In addition to this, a development for self-cleaning technology and anti-dust coating for the solar panel. Thank you.